morning, good evening, good afternoon, wherever I may be watching this from. This is Cornelius Tubinda with another segment, continuing from where we left off, that is the vector equation. Resultant vector r is equal to r naught plus t, parameter t, direction vector m. So I left off here. Now, me leaving off here might have confused a few others. So let us give an example on this diagram right here. So what we're going to do here is, let's think of r naught. R naught can be any position vector that has its tip. So get me right here, that has its tip on the scalar equation. Any position vector that has a tip on the scalar equation. Right. So an example is 2, 6. Position vector 2, 6. So we can say r naught is equal to 2, 6. Like that. That can be our r naught. Because if we move 1, 2, then we move 1, 2, 3, 4, 5, 6, we'll find ourselves the position vector that has its tip on the scalar equation. So this means that if we were to draw this, of course this is the origin here, right here is the origin. Okay. Right. This is r naught that I've drawn right here with this type of position vector. With the position vector starting from the origin here, going with its tip right there. So maybe others may be confused. Let me not draw this arrow here. This arrow is just used to show direction. So with its tip right there, with its tip on the scalar equation, this is our r naught, 2, 6. Then when we move by a certain direction vector, so think of another coordinate that has its tip, or another position vector, another r naught. Think of another r naught which has its tip along the vector equation. So you'll find that another r naught can be, r naught is equal to 4, 7. 4 and 7 right here. Now for us to move from 4 to 7, we are doing this. This is, we are at 2, 6. We are moving 1, 2. This 1, 2 is in the positive direction, and then we're moving 1 up. 1 up is also in the positive direction. Now the way we have moved to get to the nearest coordinate, the closest coordinates, is called the direction vector. Direction vector. So it means that for us to move from here to there, we are moving by direction vector s, which is, if we express in a column vector, s is equal to 2, 1 in that way. Now this s can change in its size. It can be shifted by certain, or it can be made bigger by certain scalars. So what we do is we can make it bigger by a certain parameter t. That is why there is t direction vector m. This m is simply substituted for this s. It means we are saying m is equal to s. So it means m is equal to 2, 1. So which means for us to move there to there, it is direction vector m is equal to 2, 1. That is what we need to do. So this, to move the next coordinate, is our resultant vector. Resultant vector to move to 4, 7. like that. So this is our R. So we are saying our R is equal to R naught plus T direction vector M. Right, our S was 2, 1. We moved from here, we moved 1, 2, 1, which was our M. M was also 2, 1. R naught was 2, 6 that we used. But we said let's think of another position vector, 4, 7. So we can even count from here. From this position vector, the next position vector from here to there. So let's think of these numbers here. This one and this one. So from here to there, we have moved 2. Hence the 2 there. Then from here to there, we have moved 1. Hence the 1 there. That is why it is the direction vector 2, 1. Now let's write that in the column vector form. So it means the resultant vector R is equal to R naught plus T direction vector M. Our R naught in this case is 2, 6, which is 2, 6, plus T. Just write the T like that and get your direction vector 2, 1. That is our R. Now, it's not always, you're not supposed to leave it in this format. This is the normal format we use, resultant vector R. What I'm trying to say is that actually we need to write it like this. xy is equal to 2, 6 plus the parameter t 2, 1. Parameter t 2, 1. That's what we call the vector equation. Vector equation of a line. So from this very vector equation we can get a scalar equation. And that scalar equation, what I'm trying to say is that from this very equation here, we can get this here. From this very equation. We're going to explain that in the next video. So recap of what we have done. We thought of a certain position vector and we found the example of a position vector to be 2, 6. We plotted the 2, 6 there. We called it R naught. So our 2, 6 was our R naught. And then another position vector which has its tip on the tail was 4, 7 or 4, 7. So it's had like that. Then we draw the vector with an arrow on top there. The arrow is not showing, it's like this. Trying to show that it has its tip on the line, like that. What we just did is that to move from this point to that point, we moved 2, 1, 2, and then 1 up. That is our direction vector. Now our direction vector cannot be fixed. It can change. So the next coordinate which has its tip, or the next vector which has its tip on the scalar equation is 6, 8. Reason being, we have our 4, 7 plus 2, 1, 6, 8, like that. So our next coordinate 6, 8. Again, if we add 2, 1, we'll get 8, 9. Just like that, it will keep on increasing by 2, 1, because that is the direction vector. So leaving it like this is the vector equation of a line. Thank you so much for watching. This has been Cornelius Devenda with another segment, and goodbye.